Devroy and Fant, you both are disturbing us, you know.
We're in big trouble when you are the chair.
I know, I'm terrible. Okay, so let's start. Sam is giving the next talk about fast mixing and filling. Sam, please go ahead.
Super, thank you. Thanks for inviting me. This is the first time I've been to AofA, and it's yeah, very nice to be here. Nice to see some familiar faces, but also listen to lots of talks about stuff that I'm not so familiar with, but I find it very interesting. So yeah, I only arrived yesterday. In case you hadn't seen me around, I had marking to do. I'd have preferred to be here than marking, obviously. But so yeah, looking forward to the rest of the week. So my talk is going to be more on sort of discrete probability and Markov chains, which there haven't been so many talks on that I've seen. So I'm not quite sure what people's background is. So if I'm sort of suggesting, like assuming things that you're not sure of, please just ask, and we'll I can discuss more. There's no need to get through all the slides, but I've only got 7, so it shouldn't be too bad anyway. I'd rather people, if they're confused, ask questions and we discuss, and you have some interaction rather than sort of just blast through all the material. So yes, please do ask questions if you have them. Okay, so I'll start with these parts. So the setup is going to be that we have just some finite graph, and we're going to want to color this graph. So I imagine a lot of you know about proper colorings for graphs, but the difference here is that not every vertex will receive a color. Okay, so when we color the graph, any 2 vertices that are colored, if they are adjacent, they cannot have the same color, just like in usual proper colorings. So any edge can't be monochromatic. But if we don't color a vertex, or you could think of this as like color 0 or something like this, but if you don't color it, then it can be adjacent to another not colored vertex. Okay, so if you only have one color, then your set of colored vertices is an independent set. And the model that I'll be discussing is the usual hardcore model, which some of you may know, but I won't assume you'll know. I'll be defining. And if I require all the vertices to get a color, then this is just the usual proper colorings on graphs. And we're going to have a Markov chain which is going to sample from these configurations. So we're going to look at sort of mixing time for sampling. But this is some sort of interpolation between the two. Okay, and so what's some motivation for this? The original motivation that I had, which I'll discuss a bit more later, is to do with resource sharing. So this is where you think of adjacent vertices as some sort of agents who are wanting to transmit across some frequencies, maybe by radio or something like this. And if they're nearby, they can't use the same frequency as each other. If they're far apart, perhaps they can use the same frequency, but if they're nearby, their transmissions will interfere, which is why I've called this G an interference graph. As you only get a color or a frequency if you are actually transmitting. This is why you only need the subset of vertices of the people who are actually transmitting information to form, to be the sort of properly colored subgraph. Okay, so yeah, I guess I sort of already said this. You could think of this as short range radio. The actual original motivation was fiber optic routing for like internet connectivity, which I'll talk a bit more about in detail later. But is the setup of the underlying model clear? Yeah. Okay. So we're going to do some dynamics on set of configurations that have this proper subgraph, properly colored subgraph property. It's not actually going to be Glauber dynamics, which some of you might know, but it's going to be a bit like Glauber dynamics. So just to set up some terminology, I'll say that some configuration is just elements 0 up to k, where k is the number of colors, and 0 basically means not colored. So it's proper if whenever you have an edge, the two colors assigned are different, provided the two colors are sum up to something greater than 0. So if they're both 0, that's fine. But if they're both positive, then they need to be different colors. Okay, and then the dynamics will just say, suppose we start with a proper configuration, select the vertex. This will be in continuous time, but you could do it in discrete time as well, which I'll mention after. Select a vertex v at rate lambda v, which you could think about lambdas not depending on v if you want, but just pick a vertex to update at some rate. And then when you choose this, you toss a coin to decide whether you are going to color it or not. So with probability p, you choose a color uniformly at random amongst all colors, not just available colors, but amongst all colors. And if that color is available for that vertex, which means that if you were to assign it that color, you would still have a proper configuration. If it's available, then paint it with that color. Okay. If your coin came up, 0 here, so with probably 1 minus p, then set it to color 0. Okay, so deactivate it. These decisions here are independent of the color of the vertex when you start. Yeah, so it's not like swapping color or anything like this. You can basically think of it as sort of resetting, like resampling your current color, or it's sort of it's a bit like a spin system for people who do these things, like resampling your current color depending on the colors that you see around you. Okay, and I just want to just denote the equilibrium distribution with pi, and then if I hadn't written queuing in the title, you perhaps wouldn't know why I'd wrote this as equilibrium service rates, but there's going to be some queuing theory, and this is going to be some service rates. But the point of this is what is SV? This is the likelihood that if you draw a sample from equilibrium, this is the likelihood that your vertex V will be active, will have some color that's not 0. And later active vertices will be serving their customers.
So
yes.
If K is not available, just leave it at this
yes, I guess. Yes, I didn't say that, but yes. Sorry, no, don't leave it at the same color. Yeah, set it to 0. Yes, sorry, that wasn't clear. Yes. Yes, set it to 0. Although I think the model would actually work the same probably if you just left it at the same color. But you should think of this as resampling, and then try this color. If it's available, use it. If it's not, just turn off. But yeah, sorry, that wasn't clear. Thank you. Yeah, so if you like discrete time instead of continuous time, then you could say, at each time step, choose a vertex V with probability proportional to this weight lambda of V. Okay, so are the dynamics clear? So you see, it's quite like Glauber dynamics of picking a vertex and updating depending on the neighborhood, but it's Glauber dynamics is a specific thing, which this isn't quite. So yeah, we're going to look at mixing times for these Glauber type dynamics because we want to be sampling from the configuration and actually using the Glauber type dynamics later. But so I just define mixing times carefully for I'm sure plenty of people perhaps won't know it. So we'll use total variation distance between measures, which just says that I've got some distribution mu, which I'm going to think of as my law after I've been running this process for some time, and then pi, which is the equilibrium distribution. I want to say how far is mu from pi quantitatively, and so we use the total variation distance, which says that this quantifies how much you can distinguish the two measures on a particular statistic. So you look at any measurable set. This is a finite thing, so it's anything you can measure, and you say how different is the probability. And when this is small for all sets, then we'll say that we're mixed because they're sort of statistically indistinguishable. Okay, and then the mixing time is the first time that that the law of the chain at time t is close to pi in the sense, epsilon close to pi, and then I have to say, okay, I don't know where I start from, so I want it to be uniform over all the starting states, and so yeah, then this is the first time that wherever I start from, my law will be close to equilibrium in this total variation sense. Okay, and how are we going to bound the total variation? Just for people who know about these sorts of things, we use this coupling method. So total variation, you can show that for any two distributions mu and pi, if you do a coupling of mu and pi, so just x distributions mu, y as pi, they could be correlated or they could not, but you would do them correlated, then the total variation distance is upper bounded by the probability that they're not equal. And actually, if you take an infimum over all couplings, then this is actually an equality, but we'll just use, we'll come up with a coupling. And anyone who's done mixing for Glauber dynamics and things like the proper colors and things knows that you use path coupling often to use to do this. So yeah, this basically means that we could just do a coupling of adjacent configurations. But if it doesn't make so much sense, don't worry. This is just more for people who know about these things. Okay, so the main result. Okay, so n I'll just write. Whoops. And I'll just write for the number of vertices, and x is this process. Now, we need to assume this condition, which I'll discuss in just a moment, but let's just say we've assumed this condition. Then the result is that we're close to equilibrium in total variation, and this is the bound on how far away we are. So we've got exponential decay with rate this beta here, times lambda min, where this is the minimum value that the minimum value of lambda, so the minimum rate. You could think of it lambda as just the same everywhere if you prefer, so then it's just lambda, and there's this n factor. So this term comes from the contraction rate in the path coupling, and this n comes from the diameter. Yes, Pu. P also was allowed to depend on the probabilities. Yeah, so it's the coin toss to say whether you're likely to. Yeah. So if your p's are the same everywhere and your lambdas are the same everywhere, this ratio obviously cancels, and you just get p times the degree divided by k, which is the number of colors, and you want this to be less than 1. This just comes up from the path coupling, where you want to. For people who know about path coupling, you want to have two adjacent configurations, and you do a coupling so that they get closer in expectation. And this is the I guess 1 minus this, or this minus 1 is the change in expected distance. So this is just from the path coupling technique. Okay, and then. Okay, once we have this bound on the total variation, we can deduce a bound on the mixing time easily just by setting the upper bound on the right-hand side to be equal to epsilon and solving for solving for t. Okay, people happy with that? So I sort of suggest what you might want to choose your values of lambda and p to be. So if you have some application, like maybe you're using shortwave radios to communicate, maybe like security guards at a festival or something like this, they're using radios. The graph is probably given to you by the application. It's the security point here, the security point here. These are close, but this one over here isn't close. This is given, and the number of frequencies is just whatever you have on your radio. But you can choose how fast you update your state, so you're transmitting for a while, and then you stop, and then you sort of refresh your state, and you can choose the probability of these coin tosses. So to sort of make this condition a bit more concrete, you might think that if you have a vertex in the graph that's high degree, this means it's affecting loads of its neighbors. Well, it has lots of neighbors, so it's affecting loads of vertices. It makes sense that this should update its state quite quickly because it's having a large impact. updating its state doesn't necessarily mean it's turning off. Yeah, it's just updating. So if it's off, that means it's faster till it will next be on. So it's not saying, put it on less often. It's just saying update faster, so you don't sort of have too much of an impact on your neighborhood. And if you hope that most of the time you toss the coin, you're able to find an available color, then this would suggest you're removing about the probability of you being on times your degree number of color choices, because once you're on, all of your neighbors can't use your degree, can't use your color, and you're on with probability p, so you move about p times d colors from the system. So let's make sure that's not bigger than k, otherwise you're trying to remove, you're not going to be able to really make this work if that's bigger than k. So if you take these choices of lambda, so d bar is just the average degree, so this is just so that the average rate is 1. So you choose lambda to be equal to the degree, and PV to be smaller than degree over k divided by degree. Then this condition you can check quite easily is satisfied. And this 1/3 is because I put 2/3 here. If I put 4/5 here, you get 1/5 here. And actually, a bit more, not so obviously, you can check that this equilibrium service rate, so the proportion of time that you're on in equilibrium, is obviously it's a most p because you toss the coin and then you try. But actually, this says that at least 1/3 of your attempts of finding color are successful. Why is that important? Well, I was saying, if the vertex is on with probability PV, well, it's really on with probability SV in equilibrium. So you kind of want this to be the same order. You don't want your coin to be coming up and saying, yes, choose a color, but then actually there are barely any colors for you to choose from, and you're like basically always failing to choose the color. So this is sort of saying that you're on quite a lot of the time. Any questions about this? No. Okay. So yes, sorry. Yes. No, so I'm not using, well, I guess it would be a grand coupling, but I'm really using this path coupling method. So you look at just adjacent ones where all of the, you look at 2 configurations which agree everywhere apart from on one vertex, where one vertex has one color in one site, in one configuration, one vertex has a different color in the other configuration. And now you do one step of the chain, come up with a coupling so that these two, that they try to get closer in expectation. Most of the time, they'll stay one apart because you choose some vertex elsewhere, but you try to say, I want to couple them with some probability that's larger than the probability of introducing another error. Yeah, there's some triangle inequality that this path coupling is this covers for you. Okay, so queuing. So this was this fiber optic network application that I mentioned on the first slide. I actually thought of this model when I went to a seminar given by someone at BT, and they were talking about fiber optic routing and challenges in it. And then I was doing this is during my PhD actually, and I was doing a stochastic networks course by Frank Kelly, who I'm sure plenty of you have heard of. And I thought this would perhaps be perhaps an idealized model, but an interesting sort of queuing theory version of it. So in sort of this is not going to, if people know about fiber optic routing and stuff, this is going to be not quite right here, but this is sort of the rough idea, okay, is that you send the data along these fiber optic cables, but if you want to send it from here in Bath to London, you're probably going to send it via Reading. You're not going to have a unique cable from Bath to London. You don't have like a complete graph on like the UK geography. Yeah? So you're going to go via Reading. But with fiber optic cables, you must send one like wavelength of light, one color of light the whole way. You must use the same color along the entire route. Okay, you can't send sort of blue light to Reading and then green light to London. I mean, you could do this, but you'd have to sort of decode at Reading and re-encode. And then this overhead is extremely large. If you have copper cables, you don't need to worry about this because the transition rate, time is slow and the overhead is small compared with the transition time. But now with fiber optic cables, the transition time is so fast that this overhead now dominates. So you want to use the same color. So you need to think about, you need to think about now lots of routes and how some routes might interfere. So for example, if you're sending from Cardiff to Reading, you might do this via Bath. Okay, so if someone's transmitting from Cardiff to Reading and someone's transmitting, say, from Reading, from Bath to London, the person at Cardiff doesn't know what color Bath is using to send to London, and they must use a different color. Yeah, because these two links, these two routes share a link. Okay, so this makes, when these routes can be very long, they have lots of neighbors, and this makes it very difficult to decide what color to use. And even sort of coming up with colorings can be difficult. These are people know much more about complexity theory, but I believe these sorts of things are NP hard type questions to find good colorings, and because you have such long correlations here. If you want to send something from London to Aberdeen, all these bits you're interfering with, it's just very difficult. So you can't be you can't have a centralized decision making in real time. You need some decentralization. And so the scheme that I've proposed is completely decentralized, except that you need to test if a color is available. So this is why I didn't say choose if your coin comes up positive, I didn't say choose an available color uniformly at random, because in order to do that, you would need to know the set of available colors along your entire route, which is not so realistic. It is, however, fast, apparently, to test if a color is available. So you should think of this as many colors being available. And if you test one, this is fast. But keeping track of all of them is slow. Okay, that's just what I said. But yeah, when some routes are on or on their different colors, you need to be able to reconfigure your sort of interchanges to say, okay, blue light was coming here and going on to here before, now it's doing this different route. This also can be done fast with sort of, I don't know, there is this optical switch and some engineers are very clever and they can do these things. So I'm hopefully reliably informed. Okay, but so that hopefully gives you an idea of where this sort of thing comes from. Okay, and then what is it as a queuing network? The idea is that you've got all these routes that you want to transmit data along, and let's not think about which direction they're transmitting along. So it's just transmitting data, like sharing data across this route. They can't all be active at the same time. We need to come up with some way of having some active and some not. So we use this multicolored hardcore model to do this. And then maybe along some route you've got some data that you want to send. You can only send this when the underlying configuration tells you that this route is active. So a bit more formally, you have this queue, and you change from state q, which is a vector, and this will be each vector with integer values. This says how many customers or data packets or something like this, like how many customers you have waiting to be served along this at this vertex, which is like data packets along the route. So how many customers there are at this vertex, and then it's a normal MM1 queue. Just customers arrive at some rate and they get served at some exponential rate. But now they only get served when the underlying multicolored hardcore configuration says that this vertex is active. Doesn't matter which color you are, all colors behave the same. Okay, and then the theorem does apply for the more in the paper. You can see it's on the preliminary proceedings. It was supposed to come out on Archive today, but yesterday was a national holiday on the US, so it's coming out tomorrow, which I only found out yesterday. Yeah, it does work with the more general theorem that I said before. We had this complicated condition, but yeah, I just put this simpler one. And then, okay, then in equilibrium, you look at the expected Q length at vertex V. And in particular, this is finite. Okay, so this means that there is equilibrium. Okay, so under these conditions that I've written, oh, I didn't write mu should be 1 everywhere. Okay, so every server is the same as each other. You could try to change this. You would get you could prove stuff, but it would just be more complicated to write down. Yeah, then in equilibrium you have some bound on your Q length, which I'm not saying it's particularly tight or that it's particularly exciting. Really, just the main thing is this is showing that the Qs are positive recurrent. So they aren't just going to build up and sort of diverge. They're going to come back down, and so this system is stable. And to do this, this 2n here is exactly the 2n from the bound in the mixing time. So to prove this, you really fundamentally use the mixing time because you want to know what's the chance of having of having your vertex be active, and then you can sort of look at configurations which have your vertex active, and then you want to know how likely this is, and you can use the mixing time to say if I'm close to equilibrium, then or if I'm at equilibrium, but if I'm close to equilibrium, then I can say how likely it is to have it compared with S of V, which is the equilibrium probability. And so this you can see, of course, you need the mu to be smaller than S for this to be important. I put mu smaller than a third PV because this is a lower bound on SV. Okay, so it's a bit more concrete. Clear? If I've got time just for a picture, or shall we? When do we start? Picture. Okay, so some simulations. I wasn't sure when I started whether this conference likes simulations or not, so I put some simulations in to err on the side of caution. This is just 2 graphs, each have 500 vertices, and average degree 40. The ones at the top will be Oleskey-Taylor graphs, and the ones that below will be regular graphs. So you can see this is 500 vertices. So this is just a selection of the active times, this service rates averaged over time. You can see this sort of converges quite quickly. So you can see pretty quickly you get sort of stable in how often you're active. And that's true both for the Oleskey-Taylor and for the random regular graph. Doing slightly better in the Oleskey-Taylor, but this has variable degrees, so some are worse and some are better. This one here at the bottom right seems to be kind of stabilized. Notice that this is 1,000 here and 5,000 here. Because there's a lot more steps to stabilize the Q length. So this is the average Q length over time. It looks kind of stable, apart from this one orange one, which suddenly is going a bit bad, but it's kind of stable. But even in the Oleskey-Taylor one, the Q lengths are varying quite a lot, even up to times 5,000. I did take P to be really quite large, much more than 2/3 times K over D. But yeah, just suggesting that maybe these Q lengths, if your probability of being active gets quite close to your service rate, these sort of rare times when you're inactive for a while, your Q length can build up. Like presumably this orange bit here is just when the vertex wasn't active very much, and then just some. Yeah, it looks like it still varies quite a lot. So it'd be interesting to sort of say, how long does it take for the Q lengths to sort of stabilize? Yeah. All right. Thank you very much.
Right, we have time for one question. Okay, so when the next speaker is coming, maybe another question somebody to come. Okay.
Leslie.
Here.
Did you, so you got the, path coupling mixing time, did you have the chance to, any kind of hardness for that, maybe for that service rate? I know there's a lot of parameters, but say you put the parameters roughly like that, any kind of idea whether that's optimal or?
No, and I guess it probably isn't.
Well, okay,
yeah.
probably isn't optimal, but, you know, is it hard outside or do you not get rapid mixing if you?
I haven't looked at that, but one thing I'm looking at, trying to look at with someone is the same configurations, but doing Glauber dynamics on it, like actual Glauber dynamics, and then trying to say, okay, can we use sort of the spectral independence techniques and things to try to say, you know, when you get fast mixing up to which thresholds and things like that. So looking into that.
Cool.
Okay, thank you.